Uh, but while we still have this devices in our head, let's go and tie this to IPC more cleanly. So we see that in IPC, where there's a bounded buffer, there's bounded buffer in device CPU communication. And essentially what we're doing is a remote assignment. We have some variables in the process, uh, and those variables can be assigned essentially data in device registers, or the reverse can happen. Data in the process um, can be assigned to uh, device registers, which are essentially variables in the device registers. And you have two parties involved. You have two address spaces, the device address space and the memory address space. Even though two pieces chunks of memory, they're part of the same address space in the sense that they are numbered in such a way that they're part of one contiguous piece of sequence of numbering. But they're really two disjoint address spaces. Each device has the memory in the physical device itself, not in the physical memory. Okay, they're just logically connected by the address space. So the next thing we look at next time is how we can model blocking IPC as really I/O and just see what we've learned there to inform what abstractions blocking IPC might have. Okay. And a reminder, remote assignment is a special form of IPC where the sending process or thread sends an expression which gets assigned to some variable in the receiving process or thread. And we looked at device and CPU communication, which is not quite inter-process communication, but it's still communication among um, autonomous um, engines um, working at their own pace. And we looked at specifically the keyboard and a special kind of output device, a teletype output device, which outputs things character by character. And our getC and putC calls are modeled after these two devices, the keyboard and we saw in one case um, the device was the receiver when it was an output device, and in the other case the device was the sender when it was the input device. And what we were sending were bytes. Okay. So that gave us an idea of I/O, and we're going to ultimately end up with NIO, which is going to be your assignment 6. And so that stands for non-blocking I/O. So we can see that the name NIO implies that non-blocking IPC is a form of input-output. Okay, so we understand input-output at an in-depth level, or maybe deeper than what you understood before. And let's try to make the migration towards NIO gradually. So we'll go and first see how I/O is related to IPC and how we need to embellish the basic I/O primitives to support IPC. So how can we model IPC as I/O? Okay, so I/O, we can think of there being an abstract console object, and you go and do puts and gets on this object. So we don't quite have the console object. We have maybe we have another object, and we can call that a channel object. Okay, same interface, but it's different. So it's a different class, if you will, with the same interface, and you have multiple parties involved. So when one process does a put, another process can do a get to get that character. Okay, so somehow both processes are using this channel object, and the objects have the same interface, obviously. And these two channel objects that are being used to communicate between the two processes are related in that if I do a put on my channel object, the channel object on the other end um, can give the other end the character, so the other end can invoke a getC call to get what the first process put, okay, and vice versa. Okay, so if we have a bidirectional stream. So in terms of abstractions, you are reading and writing characters that come from another process rather than from the console. Okay, so it conceptually doesn't seem very different, okay, except that we have these two channel objects that have to be somehow connected to each other, which is going to be the main issue that we're going to address here. Okay. So then another issue, which is related to the first issue I'm talking about, is what happens when a single process talks to multiple processes? Um, do all processes share a common bounded buffer? And the answer is no. If I'm sending if this one process sending its credit card information or some other information we want to keep guarded, the other processes should not be able to see that information. Okay. So a single process could be interacting with multiple channel objects at the same time. Okay. So then the complication is, how do we dynamically create channels? And then the next question is, how do channel objects get connected to each other? Okay. So we do need to have channels connected to each other, and if we want to allow a process to talk to multiple processes, we also need dynamic channel creation. And this is an issue we did not quite face when we were looking at console input output. This should not be channel, this should be console here. Because in that case, we had a single input and output that is bound to a process. So the process doesn't have to create it, it's given to it by the operating system. So there's no abstraction needed to create the object. But even in non-distributed applications, you can argue that we need multiple read-write streams. Okay, so the console and channel can both be united into a common abstraction of a read-write stream. And we do need to, even in non-distributed applications, have multiple read-write streams. If you ever interact with files, then you can have multiple files open, and you can be writing to multiple files and reading from multiple files, as well as reading from the console or writing to the console. So having multiple channel objects or stream objects is not a big deal. Uh, it's not a special capability we need to provide to support distributed communication. So and we know of some abstractions to create these streams dynamically. For instance, in Java, you can say open on a file object, and or I think this is more abstract, that you can imagine some file object, and you invoke an open call on it, and you get a stream that's connected to that file. Okay, so a particular process can talk to multiple file stream objects. This is abstract. This is not actually Java. And whenever you are interacting with some external source of information, we need to make sure that we have rights to that source of information. So there's access rights associated with files. Okay. So we still we still haven't quite answered how we can translate this to interprocess communication, and access rights raises an issue. How do we make sure that that only processes with the correct rights can listen to two connected channels, or processes that are desired, uh, uh, that are authenticated in some way, um, can actually connect to somebody's channel. Okay, so there might be one process that has a channel endpoint, and that needs to be connected to other channel endpoints, and we may not want arbitrary processes to talk to its to connect to its channel endpoints. And once there's a connection, we want to make sure that it's private. The second question is kind of easy, that once there's a connection, the system can make sure that that connection is private. So the first question is a little bit, requires some application involvement. And we can try to not have application involvement and have rights associated with channels. But rights are always enforced by an operating system. So when there are processes of different operating systems, there is no common authority to make sure that these rights are obeyed. So what to do in that situation? And the answer is that both processes have to take explicit actions to connect their channels to each other. So if a process doesn't want to connect to another process, it just doesn't take that action. So that's the access control issue. Now the other issue is how does one process, how do these processes name each other's channels to connect? And we want to keep the awareness in one process about the details of the other process as little as possible, as we saw. So does each process have to know about the other? And we've seen earlier that no, the process that has no awareness of the other parties does not have to have awareness, is the server, and the other processes are the clients. And of course, once the server can have some awareness and enforce an access control, but it doesn't need to have awareness. And it can also control what messages are sent on a channel based on some authentication provided by the connecting process. Okay, so the connecting process can connect, say, this is who I am, do you trust me? And it says, yep, I know your login and password, so I'll continue connection. So we've seen also that there are external names, and the names can take various formats. They can be distribution aware or not distribution aware, location aware or not location aware. And so if they're external names, we can connect them to channels, both to the and so that's how one client can connect to another client. So we're going to assume what we see today um, commonly with sockets, that the external name is the host name and a single port number. Okay. So a server can go and is always executing some host, so we know what host it is. I mean, so the client can know what host it is, or find out through a name server what host the server is on. And it can also find out through a name server what the port number is, and it can then connect. It can use that host and port number to connect its endpoint to the server endpoint. And this is like, you guys coming to a particular room, so you don't have to I don't have to know about your details. I can just go and give you the room number, or or a URL for virtual class. So it's a very similar concept. Okay, so the tricky issue now arises. um, the server a client goes and uses a host and port number. Each client would want a private channel to the server. So does that mean that the server has to have a separate port number for each client? And if it does, then it means somehow it has awareness about each client, okay, because it knows this is the number that the client is going to talk, use. So we cannot support an arbitrary number of clients, and it implies client awareness. So the question is, how can we have a single port number and yet be able to create multiple private channels to a server? Okay, and if you've ever used distributed communication before, you know the answer. And if you haven't, you'll have to use your imagination. But this is where those of you who've done networking should have an edge. And a lot of you who haven't done networking also have done some distributed communication. So think about this question now. The server is running on a host. It has a single port number, and yet it's possible to have multiple private channels connected to its channels. So what's going on? What else do we need? Or how can we use what we already have to establish multiple private channels? Okay, so that's the question for you. And so so we need this two-phase connection, as you guys mentioned. And in this first phase, we somehow the client goes and sends some credentials to the server. It doesn't have to be their cookie or some unique name. It can just be their host and some automatically created port number that identifies them. And the question really is, what the first phase, what operations do we really have, and conceptually, how are they similar to something we might have seen before? Okay. So, so we're going to have a connect operation on our channel that's going to start the first phase from the client side. Okay, so this is before you do any get C or put C, you do a connect. This is the first phase. And we're going to have two kinds of channels the server has. Okay, this is what I was trying to get at. And the first channel is used for the first phase, and then the subsequent channels are used for the second phase. Okay, and there's going to be a single channel in the first phase, used in the first phase. And that channel is bound to the port number that's identified. Okay, and then other channels are going to be created dynamically, and then yes, you can imagine having some anonymous port numbers to identify them, but those are not advertised. Okay, those are only used internally. So this initial channel is going to be essentially a factory channel. It's going to be used to create other channels. So what's often confusing about sockets is that the client uses one abstraction for both phases. And I think that's what confuses people, even those who've used sockets before. And connect call on the channel object sends a message to the server socket channel, the factory channel, and the put C and get C send messages to another channel in the server, which is created dynamically. Okay, and the connect call sends this message basically saying, "Give me a new channel, create a new channel, please." And the server goes and sorry, so the server goes and first creates this channel from some using some static method. Okay, and there's only one of these channels per port number. Okay, so it does it only once. Okay, so and so my so uh, there's a static method, and then there's these instance methods later. Okay, so the server's factory selector, if you will, is the one that goes and creates this factory channel. Okay, so we got the factory channel from another factory, which is the server factory selector, which is a local factory. The server channel factory that we have is a remote factory. Okay, so once you get this object, the server can go and say, I want to receive messages sent on this particular channel. And like I said, there's only one of these channels per port number. Okay? And the connect message that goes from the client goes to this particular factory channel. So now we've got a distributed factory to which we are sending messages. Okay? And this channel then goes, and whenever a message comes in, it creates the actual channel that the client will use for private communication. This is the channel that will be the destination of the put C and get C calls. That will be the one that's connected to the put C and get C calls in the client. Okay, so now, and that's what's happening here. So it works very nicely actually, because we've got only one port that's advertised, and what's happening internally we don't really care. But once we have this two-phase communication, the second phase doesn't have to be it has to be demultiplexed at some point. The anonymous port numbers, messages have to go to the right port client. Well, we are going to use the same factory channel, except we're going to do another accept. After the first accept, the server does another accept in a loop. Okay, it keeps accepting till it decides no, it won't accept any longer. And again, the other client sends a message which goes to the same factory channel, but we get now a new private channel, and messages now from the put C and get C calls now are bound to the get C and put C calls of another object. Okay, so this is really what's happening, and we've gone and changed the abstraction. We are not just focusing. We don't just have put C and get C. We also have connect and accept calls, and we don't just have one kind of channel, one kind of object. We have two kinds of objects. In the server, these objects are distinguished. One is one is a channel factory, one is a channel. These are my names. They don't, when so the API, the documentation of sockets don't mention the word factory, but I personally think that it's more clear if you call it a factory channel because it creates other channels. And again, like I said, the confusion arises because the same object on the client end is being used to communicate with two different objects on the server. So server accepts in a loop with each accept returning a new connected channel. And you can imagine why you would need, you know, multiple threads here. We could have one thread that's looping, doing accepts, and you can have other threads um, for each of the private channels. Though you don't have to have multiple threads. Okay, so when we look at non-blocking I/O, we can see that it can all be done in one thread, and that's more efficient in terms of thread creation. So we see that there's only one advertised port number. There are these temporary port numbers that are created to multiplex messages, but there's only one advertised port number needed to have multiple clients talk to a server. So does it ever make sense to have multiple numbers per server? And usually servers have only one port number. So this may be a subtle question, but I'm just curious. I'm going to give you an example, but I'm curious, you guys have creative minds. I'm curious whether you can think of a reason why you might have the same server have multiple advertised port numbers. So can you think of an example of a server with multiple ports? Multiple ports meaning multiple advertised port numbers. Okay, so my thinking is warped or influenced by the things I've built. So let's talk of the grading server that we've had. And again, this same server has been used for both 401 and for multiple ports. Well, this is something we've actually built. So we might have, a single port for all clients, um, and messages come into the server for grading, and it doesn't really do the work itself. It goes and sends the work to other processes that have connected to it. So the actual work is being done by these slaves, and they've connected to it and said, "Hey, I'm willing to do the work." And so this is again like Leo's mentioned, and in our implementation, the COM401 grader and COM533 grader are local processes in the same machine as the dispatching server. So indeed, we have a different port for local processes, and the graders provide modularity and load balancing. And dispatching server has separate ports with different visibility for clients and graders. Uh, and then the question becomes, is the grader a client or server? And we saw that server or client distinction depends on awareness, not on sort of who's providing the service. So you can argue that the grader is the one that's providing the service. Yes, it is. Yet it is the client of the dispatching. So dispatching server is fixed point. So slave graders are clients but provide the service. So this is an important issue. But like you guys mentioned, Nolan mentioned that for legacy reasons, we might have one port for unencrypted traffic and one for encrypted traffic, and like Leo also mentioned that we might want to give higher priority to some processes so they can use a separate different port number. So we see that the migration of I/O to IPC involves using putc and getc on regular channels, and also involves factory channels with accept and connect is really an operation on a factory channel, even though it's routed through the channel object. Okay? So we've seen now two other operations. So we understand I/O, we understand how I/O is connected to IPC, and now we want to look at a finer grained issue. And not all IPC, how it's connected to remote assignment IPC. And now we want to look at a finer grained issue, which is, do we have blocking IPC or non-blocking IPC? And that's going to distinguish the socket usage that you've done in 431 or 524 was the course that I taught, and the implementation you will do in assignment 6, which will be non-problem.